In this video, we're going to look at exponential functions. So an exponential function basically is something that can be written in this form. A constant times another constant raised to a power x, where x is your variable. So in this example, we want to find an exponential function that has these two properties. If I plug in a 2, I should get out 6, and if I plug in 4, I should get out 24. So let's write down what those two conditions are saying in terms of this form, a times b to the x. So first of all, when I plug in a 2, that would give me a times b squared. And when I do that, I want the output to be 6. And then if I plug in a 4 for x, that gives me a times b to the 4th, and the output of that should be 24. So I have two conditions, which makes sense because I have two unknowns, a and b. So together, these two conditions represent a system of equations we can use to solve for the two unknowns. There are several ways to approach this. For this kind of problem, here's a nice little trick. What I'm going to do is eliminate one of the variables by dividing one of the equations by the other. Notice that if I take this quantity, a times b to the 4th, and I divide it by this quantity, a times b squared, ab to the 4th over ab squared, what's going to happen is these two a's will cancel out. So I won't have any a's left. Now first, before we do that, let's finish setting up the equation. So I take the entire second equation, ab to the 4th equals 24. I divide that by the first equation, ab squared equals 6. So on the left side, I'm dividing by ab squared. On the right side, I'm dividing by 6. This is just like problems from algebra where you subtract one equation from another. This time I'm dividing one equation by another. And so I get a new equation. And like we said a moment ago, we can get some cancellation to occur. Actually, we can do even better. Notice that I'll have b to the 4th divided by b squared. That will simplify to just b squared over 1. On the right side, let's simplify. 24 over 6 is 4. Okay, so I'm really looking at the equation b squared equals 4. And there are two solutions to that. B equals 2 or b equals negative 2. But here's the thing. For an exponential function, we always want this base b to be a positive number. You can never have a negative base in an exponential function. And that's because you run into complications when you try to take fractional exponents of negative bases. That corresponds to taking roots of negative numbers. And to do that, we'd run into complex numbers and lots of complications. So we will only ever use a positive base for the number b in any exponential function. Okay, we found one of the two unknowns, b. Now I can use that to find a. I'll plug it back into either one of these two equations, and typically you want to go with the simpler equation. In this problem, it looks like that's going to be the equation that has the smaller exponent. So a times b squared equals 6. 2 squared is 4, so I'm looking at 4a equals 6. I divide both sides by 4. I get 6 over 4, which we can simplify to 3 over 2, which of course would be the same as 1.5. You can write it either way in this problem. I now have a and b, so I can put it all together to write down the exponential function. In this case, f of x is 3/2 times 2 raised to the power x. One more thing I want to point out. When I set this equation up, I chose to put the power of b that was larger in the numerator, right? So when I divided one equation by the other, I put the larger power in the numerator. And the reason for that is that way after we canceled, we got a denominator of 1. which made things simpler. So that's a good thing to keep in mind. Let's look at another example. Find an exponential function that satisfies f of 0 equals 6 and f of 2 equals 3. So let's again plug in these x values into the form ab to the x. Ab to the 0 should give me 6, and ab squared should give me 3. This is my system of equations to solve. Now actually this time I'm going to use a different approach, because I notice that b to the 0 simplifies, right? B to the 0 is the same as 1. So this first equation can actually be written as a equals 6, and we've already found one of the coefficients. So keep your eyes open for opportunities to do that. Now I've got a, so I can plug it into the second equation. Instead of a, we'll write 6b squared equals 3. So b squared equals 3 over 6, which simplifies to 1/2. And again, that has two solutions. That quadratic equation has the solutions b equals square root of 1/2 or b equals negative square root of 1/2. But since b is the base in an exponential function, we cannot use a negative number. So that means we're stuck with b equals square root of 1/2. And now I can write down my formula for the exponential function. F of x is a times b to the x. Here's another example, finding an exponential function, although this one's written a little bit differently. Notice instead of a times b to the x, we have a times e to the kx. So remember, e is not an unknown. E is Euler's number, which is about 2.718. But we have to leave it in the exact form e because this is just a decimal approximation, and you really don't ever want to plug in decimal approximations into a problem like this when you're trying to solve for some other value. So we're just going to leave things in terms of the number e. So our unknowns in this problem are the coefficient a and this coefficient k. Those are the things we have to solve for. Let's start this just like the previous questions, where we plug in the inputs and set the results equal to the desired outputs. So first I plug in a 1, and I get a e to the k times 1 equals 6. And in the second condition, f of 2, that becomes a e to the k times 2, which should equal 18. Okay, so here's my system of equations to solve. Let's use the trick again where we divide one equation by the other. I'm going to take the equation with the larger exponent and put that in the numerator. So a times e to the 2k is in the numerator. A times e to the 1k is in the denominator. And of course, it's not necessary to write a 1 here, but I'm doing it anyway for clarity. On the right side, the corresponding fraction, the numerator would be 18, the denominator would be 6. And let's simplify. We can cancel a's on the left side. And we can also do a little bit of simplifying with the exponential term. Remember, there's a property, if I have x to the a over x to the b, that can be rewritten as x to the a minus b. So if I do that on the left side here, e to the something divided by e to the something, that can be written as e to the difference, 2k minus 1k. On the right side, 18 divided by 6 simplifies to 3. Okay, now we can simplify some more. 2k minus 1k is just k. And if I want to solve for k here, the way to do that is to use a natural log. So I take a natural log of both sides, because a property of logarithms allows me to pull this exponent k out front and turn it into a coefficient. And the reason I use the natural logarithm instead of some other base is because natural log of e is exactly equal to 1, which means I've found the value of k here. K is natural log of 3. So now I know k. I can plug that back in to one of the equations to find a. Let's use the first of these equations because it looks simpler with that smaller power. A times e to the k, but k is natural log of 3, times 1, let's not write times 1 now, equals 6. Now what's nice here is e raised to the natural log of something. The exponential and logarithm functions are inverses of each other, so because we're raising the base e to a log base e, those cancel each other out, and we get a times e to the natural log of 3 is just 3. Now we can isolate a. 6 divided by 3 is 2. So I have a, I have k, and now I put those together and I write down my function. F of x is a e to the k times x. Let's look at a couple of word problems. These look different, but they're really pretty much the same kind of questions as the ones we've just answered. We just have to take the statements that are given as sentences instead of equations, like f of 2 equals something. We just have to interpret that information out of the sentences. So a bacterial culture begins with 200 cells. That's going to be a piece of information. If I think of my function as a function of time, it begins with this amount, so when the time elapsed is 0, f of 0, the value of this population function is 200. And then after 40 hours, when 40 hours have elapsed, f of 40, the number of cells has doubled. So instead of 200, we'll have 400. So now it looks just like the sort of problem we were looking at earlier. With a bacterial growth problem, a population growth problem, typically we're going to use an exponential function, unless we're told to use something else. And we're not here, so let's write down an exponential function. F of x is, let's use the simpler form, a times b to the x. And let's evaluate a and b by taking these two facts and turning them into a system of equations we can solve for a and b. So if I plug in a 0, I get a times b to the 0 equals 200. And if I plug in a 40, a times b to the 40 equals 400. Solve that system of equations. Now you'll notice that it has a familiar form to the second example we did earlier. B to the 0 is 1. So this first equation is telling us right away a is 200. If I plug that into the second equation, I have 200b to the 40 equals 400. And if I divide both sides by 200, b to the 40 equals 2. And then I want to isolate b, so I have b, if I want to undo a 40th power, I do that with a 40th root, or equivalently a 1 over 40 power. So I do that to both sides, and I get 2 to the 1 over 40. Now I have a and b, so I can write down a formula for my exponential function. F of x is a times b raised to the x. Now that's not the end of this question. There was one more part. How long will it take before there are 1,000 cells in the culture? So we want to do one more thing here. We want to know when will this equal 1,000? So that gives us another equation to solve. 200 times 2 to the 1 over 40 raised to the x equals 1,000. So we're trying to figure out the value of x. X represents time elapsed in this question. How much time will have elapsed before we have 1,000 cells? So we start solving for x here. I'll divide both sides by 200, and I get 2 to the 1 over 40 raised to the x equals 5. And then I have a variable in my exponent, so I'm going to bring that out front using a logarithm. I can use any logarithm I want. I like natural logs, so let's use that one. Natural log of 2 to the 1 over 40 raised to the x equals natural log of 5. And then bring the x out front. X times natural log of 2 to the 1 over 40 equals natural log of 5. So now this is just x times a number on the left. I can isolate x if I divide by that number. So I have natural log of 5 already on the right, and I'm going to divide that by natural log of 2 to the 1 over 40. And you can use a calculator to evaluate this quantity. Approximately 92.8 hours. One more. A population grows by 10% each year. Find the amount of time it takes this population to double in size. So this is a lot like the previous question, except we were not specifically told exactly how many rabbits we have to start with. Or does it matter? Well, not really. So notice that if I have f of x equals a times b to the x, my starting value, a times b to the 0, is a. But if you remember the way that we solved a lot of these problems, we end up canceling out the a when we're working with that system of equations. And maybe we'll be able to do that now. Maybe we'll be able to figure out exactly how long it takes to double without knowing a if we're able to get it to cancel out. So that's what we're going to try to do. Now, do we know b? And it might not look like it, but actually we do, because we're told that the population grows by 10% each year. And so that's a standard way of describing the base in an exponential. The base is 1 plus the growth factor. In this case, the growth factor is 10%, which is the same as 0.1. And so our base is really 1.1. So we already know b. So we can write f of x is a times 1.1 raised to the x. And we want to know how long it'll take to double in size. Well, the initial size, when you start at time 0, your initial size is a. So if it's doubled, the value will be 2a. So we end up wanting to solve a times 1.1 to the x equals 2a. And that's perfect, because I can divide both sides by a and get the cancellation we were looking for. Now I have 1.1 raised to the x equals 2. We'll solve that equation using logarithms. I'll take a natural log of both sides. Natural log of 1.1 raised to the x, and natural log of 2. Pull the x out front and get x times natural log of 1.1. And then we can isolate x, divide both sides by this number natural log of 1.1, And this is an exact value, but we can get an approximation for that. If we evaluate natural log of 2 divided by natural log of 1.1, we get approximately 7.27. And our units of time in this problem are years. So with a 10% annual growth rate, we expect the population to double in size after a little more than 7 years.